I welcome you all in this lecture on generation of system equations, which is a sub module for modeling and simulation of dynamic system course, which you are going through. Now, as I have discussed in my earlier lectures, that the greatest advantage of bond graph modeling is that it can be used for modeling of systems which are there in the multi energy domains, and the system equations can be generated in an algorithmic way. Okay. So, let us see now if the system equations are to be generated, the first question is that the system equations are generated in terms of what. Okay. So, the question of selection of system variables arises. Now, you see a system changes from one state to another because of the absorbed cost. So, if I define say absorbed cost as integration of cos dt, of course, integration being carried out from minus infinity to t, then it is the absorbed cost which is responsible for change from one state to another state. Okay. So, what we will first do is that we will identify the system variables or the variables in terms of which we can write the system equations. So, let us look at say element I. Now, if I write the expression for I element, then you see that the momentum is integration of the effort. So, here going by this definition of absorbed cost, we can see that the absorbed cost is the momentum here for the I element. Likewise, if we see the C element, then in case of C element, this is our expression which is going to be, and here it is the flow which is being integrated in order to get the displacement. Fine. So, it is the Q which is the absorbed cost, okay, here. So, the system variables you can see are P's and Q's, that is momentum and the displacements. Of course, if I am talking about a mechanical system. So, the system variables are P's and Q's of the integrally caused I and C storage elements. Okay. So, whatever system equations will be developed in during bond graph modeling, these system equations will be in terms of the P's and Q's. Now, as I have been talking to you that we get system equation in algorithmic manner. Okay. So, what could that algorithm be? Okay. So, here the system equations may be generated by answering the following two questions or two logics if we implement. The first one, what do the elements give to the system, and of course, whatever they are giving to the system, it should be expressed in terms of system variables. So, that is the first logic which we are going to use. The second logic is that what does the system give to the storage elements with integral causality. So, if we implement these two logics, then we can get the system equations in terms of the system variables, and once we have the system equations, then we can use those system equations for the simulation purpose. Let us take an example of mechanical system. Okay. The figure which here you are seeing is a simple spring mass damper system which has been subjected to a certain force excitation. Okay. Now, the question is that first of all we need to understand how can we draw the bond graph model for this system. So, before I will be talking to you in much more details when I will be discussing the modeling of the mechanical system. Okay. That is, I will be talking about how do we draw the bond graph for any generalized mechanical system. Okay. But to be precise here we can see that the spring and damper other end is fixed, okay, that is they are inertial. So, it implies that the mass, spring and damper this end they are all moving with the same velocity, fine. So, as we have seen the general procedure, first we identify what all elements constitute this system. Okay. So, here as you can see that the elements what we have is we have a force which is acting on the system, we have a mass, we have a spring and we have a damper. Okay. So, these are the 4 elements which constitute the system. Then what we do, we can represent the virtual power pipelines, okay, through which power flows to these elements, all right. And after that we can put the constraints. Now, here as I said, you can see that all these 3 elements are going to have the same velocity here. So, plus the force as well. So, here we can put a constraint of 1 which is the constant flow constraint, okay. And of course, after this we can put the power direction which is as good as fixing of the coordinate system in our conventional mechanics, and after this we can causal this bond graph. In the last module we have seen how to causal the bond graph. So, for causaling purpose we see that this is the force, okay, which will be represented by say source of effort here. The mass is of course an inertia, the compliance here will be represented by K, and of course, here damping which we represent by R. Fine. Now, coming to the causality, as I was telling, first we causal the sources. Okay. So, this is source of effort. So, it will always be giving effort to the junction. After causaling the sources, we can causal the storage elements. Okay. So, for I element this is the integral causality, whereas for the C element this is the integral causality, that is it takes flow, returns effort, and I elements takes effort and returns flow. Now, this junction is a constant flow junction. So, if you look at the causality of the junctions, then we can see that this flow has to be decided by any one of the bonds, and I is already doing that. It means that the R here is going to have the stroke here. Okay. So, that is the R element will be giving the effort to the junction. So, this way we can create the bond graph for this system. Now, after creation of the bond graph, we have to identify the system variables, that is the variables in terms of which we are going to write the system equations. So, here see for the I element here the variable will be momentum of that. So, that is P3, and for the C element the system variable will be Q2. Okay. So, this way we have, that is it is the displacement of the spring and the momentum of the mass, these are going to be two system variables in this case. Now, after this we go by the same logic. Okay. The logic which I just discussed in my previous slide, that first logic is what do you the elements give to the system, what do the all elements give to the system. Okay. So, here let us look at this, the I3, I here, I element 3 means that it is the bond number 3. So, I3 is giving to the system a flow, here you see that there is no stroke, it means that it is giving it a flow, and that flow F3 we can write as P by m, that is momentum by mass. So, we will be getting that as the velocity. So, F3 is P by m. Then the next element is C element, that is C2, it is giving an effort here. So, that effort I can write E2 as K into Q, where K is the spring stiffness constant. Okay. And the damper R4 is giving the effort here. So, that effort E4 I can write as R into F3, and you see it is a constant flow junction. So, whatever F4 is there, it is same as that of F3. So, I can here I have directly written it as RF3. Okay. So, this RF3, then I can substitute for this F3. So, I can write this as RP by M, and SE will be giving an effort, and in this case it is the force. So, SE E1 is equal to Ft, fine. Then we go for the implementation of the second logic, and the second logic is what does the system gives to the storage elements with integral causality. Okay. So, first of all we need to identify which are those storage elements who have the integral causality. So, here it is the I and the C, these are the two storage elements who have the integral causality. So, you see that the system is giving to this I element an effort, you can see here the stroke is there, it means that it is giving an effort E3. Now, this E3 I can write as E1 minus E2 minus E4. Of course, this relation comes from the basic concept of conservation of the power as we have seen earlier, and since it is all the bonds are connected to a constant flow junction. So, flows are going to be the same. So, here basically what we will be having rather that it will be E1 is equal to E2 plus E3 plus E4, and from here I am interested in finding out E3, and so this will be E1 minus E2 minus E4. So, this is what is going to be. Now, this E3 I can write as P derivative, that is the derivative of the momentum. E1 I have already seen it is Ft here, E2 I have seen it is Kq, and E4 I have seen that it is Rp by m. Alright. So, this is my first equation, fine. Similarly, I can find out that what does the system is giving to the storage element C. So, if you look at here, the system is giving to the storage element C a flow, okay, and that flow is F2, and again this F2 will be same as what the derivative of the displacement, that is q dot, and this q dot we have already found out that is going to be equal to P by m, because this is flow and this element is connected to the constant flow junction. So, the flow here is going to be the same as this one. So, this q dot is P by m. Okay. So, we have these two equations for this system. Okay. These equations are P dot is equal to Ft minus Kq minus R P by m, and q dot is equal to P by m. So, here we can see that these two equations are written in terms of system variables, that is momentum and displacement. I can write these equations in state space form, and that is I can write here P dot Q dot is equal to our A matrix of the state space formulation, and then we will have P Q here plus the input vector here. Fine. Now, here you see that the coefficient of P are minus R by M and coefficient of Q are minus K, and here this is F t. And for the second row, Q dot is coefficient of P is 1 by M, and here this is 0, and of course, in this there is no input, so it is 0. So, here we can see that we get this equation in the state space form. Now, you see that we are more conversant with the equation in this form in terms of displacement, that is m d square q by dt square is equal to minus r dq by dt minus kq plus f t. Alright, so that we can get if we substitute for p in the first equation. Okay. So, if we substitute for p in the first equation, then we can get this expression, or finally, it is this equation that is m d square q by dt square plus r dq by dt plus kq is equal to f t, or as I said, this is very similar to what we are more conversant with our vibration course, that is m x double dot plus r x dot plus k x is equal to f t. Okay. So, this is how the system equations are derived using these two logics in the bond graph. So, we can see that the derivation of the system equations we have algorithmized. Okay. Next, let us take an example of a electrical system. Okay. The previous case we have seen example of a mechanical system. Now, let us see an example of an electrical system. Now, in case of electrical system, the causes to integrally causal I and C elements are the voltage and current. Fine. So, voltage and current are these are the causes. So, the observed causes are the generalized momentum and the generalized displacement, that is charge. So, the equations in electrical system will be written in terms of generalized momentum and the charge. So, the system variables will be generalized momentum P, which is integral of e dt, and which can be written as L I, where L is the inductance and I is the current, and the generalized displacement or the charge Q can be written as integration of I dt. Now, let us take an example of this circuit. Now, the thing is that first we need to draw the bond graph model for this circuit, and then we need to causal it, and after causaling using those two logics which I have just told you, we need to derive the system equations. Okay, and that is going to be the aim of this one, this topic. Fine. So, to derive the bond graph of this system, you can see here that this system composed of a voltage source, a resistance, here inductor and capacitor are in series, and again here inductor and resistor they are in series, and of course these two are there in the parallel. So, to derive the bond graph model for this system, we can use the concept of masking which is there in the bond graph, and I will quickly explain you how can we draw the bond graph for such a system. So, we have a resistance here, an inductor, then there is a capacitor, and again an inductor, and say there is a resistor. Okay. So, this is voltage source E, we have resistance R1 and inductor L1, capacitance C and inductance L2 and the resistance R2. Fine. Now, you see here voltage source and this resistance R1, they are in series. Okay. So, suppose I for the moment I just mask this portion, then what happens? I have this source, resistance and something in series. I do not know what this something is. Okay. So, what I will do? I will put a SC element SC and a resistance R is equal to R1, they are in series, plus something is there that I am not aware of. Okay. Fine. Now, here in this something you can see that there are two things, this inductor and capacitor, say they are in series, and again this inductor and resistor, they are in series. So, if I take this as one element, then I say that this and these two envelopes, they are in parallel. Okay. So, what I do? I put a 0 junction, okay, because parallel means they have the same voltage or the same effort. Okay. So, the 0 junction here and here I put for these two. Okay. Now, you see here inside of this the inductor and capacitor are in series. So, the constant current. Okay. So, here I put a one junction and here I just put I is equal to say L1 and here I put say C is equal to 1 by C. Likewise, here inductor and resistor, they are in series. So, I can put one junction here and then I can put say I is equal to L2 and R is equal to R2. So, this way I can draw the bond graph model for this system. Okay. So, in fact, this is same as this one, just a little this portion has been put here at the bottom and this portion has been put here at the top. Fine. And then of course, we can causal this. So, causaling as per our concept, what we have done, first we causal the sources, so source of effort, so it will be giving effort here. Then we causal the I integral causal I and C elements. So, I causal I here, I causal C here and I causal I here like this. Okay. And after that we do the causaling for the rest of the bond graph, so that the whole system is integrally causal. Okay. Now, here you see that this is giving flow, this is effort. So, this junction is determined. So, I can put it effort here. Okay. So, effort is here, you have flow here, fine, all right, and here effort. So, here flow, this is one junction. So, this has to bring give effort and here also effort has to be there. So, the flow here is fixed, flow here is fixed. So, and this is a 0 junction. So, this has to be determined by someone. So, that information has to come from here. Okay. Now, from flow is coming here. So, this has to be causal like this. Okay. So, this way we can causal the bond graph. Now, let us see how do we derive the system equation. Okay. So, again we go by the same logic, what do the elements gives to the system, the first logic. Okay. And here for bookkeeping purpose we number the bond graphs. Okay, we number the different elements of the bond graph. So, this number is arbitrarily, you can have your own numbering scheme for this. So, first what do the elements give to the system? So, let us first try to see what all elements give to the system. So, you see this is I2 and this is giving flow. So, I can write F2 as P2 by L2. Okay. So, this is I2, then we have the C4, this is giving effort here, and this effort I can write, or voltage I can write Q4 by C. Okay. And the I5 here, this is giving flow, and I can write this F5 as P5 upon L1. Then the R3 here, we can see the R3 is giving an effort. So, this effort I write E3 as R2 F3, or this is R2 F3 is same as F2. So, I put F2, and what is F2? It is P2 by L2, I have just derived in the previous slide. So, this way I can write E3. Likewise, my R6 is giving an effort E6. So, this E6 is what? R1 F6. Now, what is this F6? This is same as F7 here, and what is F7? This is F8 plus F9. So, F8 plus F9, and here what is F8? F8 is determined from this one F5, and F9 is determined from F2. So, F5 plus F2, and then I can substitute values of F5 and F2 as P5 by L1 plus P2 by L2. Then we go for the second logic, that is, what does the system gives to the storage elements with integral causality. So, you see here the I2 to I2, the system is giving effort. Okay. So, this E2 I write as P2 dot, and this P2 dot is E9 minus E3, and E9 is same as E7 here, because this is constant effort junction. So, E7 and E3 we have already found out, which is R2 P2 by L2. Okay. So, that is there. Now, further this P2 dot I can write E7. Where is my E7? This E7 is E1 minus E6. So, E1 minus E6 I put, and then I put the value of E1 and E6 here, then I get this equation. So, E1 is my what? E1 is SE, this one sorry, E1 is yes ET, and E6 is this value. So, this way I can find out the P2 dot. Next, to C4 the system gives flow, that is F4, which is Q4 dot, and this I can write as P5 by L1. Okay. And to I5 the system gives effort, that is E5 or P5 dot, and this E5 is E8 minus E4, and E8 is same as E7, and E4 I have already found out Q4 by C, and what is my E7? That is E1 minus E6. This is there, I substitute the value of E1 and E6 here, and this way I get the P5 dot. So, I can write the state space equations in terms of system variable P2, Q4 and P5 as this one. Okay. So, here you can see that this is the input vector, this is the vector corresponding to the system matrix, and this is the A matrix of the state space form, and this is the system variables derivative. Okay. So, this way we can derive the system equations, and these are the references. Our book is there, and there is a book by Professor Mukherjee, which one you can go through for further understanding of this topic. Thank you.